So, okay, so let me just say hello. Now we're officially recording. And just I want to say before you start, Matteo, that as you may have seen in the course webpage, we are following Nicole's suggestion. We're making this kind of grid of nice selfies of people watching the course. So if you want to take a selfie of yourself watching the course, send it to me and I'll post it on the website, and then we can also post it on social media and so on. So Matteo, thank you very much, and yeah, you have the stage.
Okay, thank you, Gabriel, and thank you all for coming. So welcome to this second class, or this second part of the course. Today, we're going to talk about the role of quantum coherence in thermodynamics. But first of all, I would like to give you a quick recap of what we saw in the previous class. So we introduced the notion of thermal operations and thermal processes. One being a notion which is somehow more constructive, and the other one it's more manageable and easier mathematically, but it's also founded on clear principles. And anyway, whichever of the two you choose, basically everything is going to work essentially the same. And the kind of question that we looked at is, what's a set of possible transformations that can happen during one of these thermalization processes? We saw that these thermalization processes contain a lot of different kind of physical models, from more standard thermalizations to, for example, the James Cummings model. And sorry, just a second, my cat is playing with the Christmas tree ball. I'm back. So we studied this set. So we wanted to know which are the yeah, exactly, which are the set of Qs that you can reach through one of these processes. So these P and Qs are just the probabilities of occupations of different energies. And we saw that this problem, which is quite complicated in principle, can be actually simplified down to just a problem of knowing what's a set of Qs that thermomajorize that are thermomajorized by P. Okay, so the other way around. And we studied this notion of thermomajorization, which is an extension of the notion of majorization, and we saw that it's basically you can check if one probability is thermomajorizing another by constructing a curve, which is called the thermomajorization curve. How do you go about constructing it? You first need to take your probability distribution and you order it in a way that it's sorted by Gibbs reweighting. So you want to find some reordering of the indices such that P divided by the corresponding Gibbs weight is ordered. So in this way, as in this equation. And once you have done that, you just put in the x-axis just the partial sums of these Gibbs weights. So in this case, just the sum from I to k of these Gibbs weights that are here in the denominator. And as y's, you just take the partial sums of the probabilities. So in this way here, for example, I've got the first point, which you do by, which is just x1 being e to the minus beta e to the, of pi 1. And the probability is just p of pi 1. And then the second point is just the sum of the first two Gibbs weights, sorted according to this order. And here you have the sum of the two probabilities and so on. And then you just do the piecewise linear curve that joins these points. And this is the thermomajorization curve associated to P. You do the same for Q. And then you transform the problem on knowing if you can have a thermalization process from P to Q, which is some non-equilibrium transformation, to just a relatively simple problem, which is to check if the curve of P is all above the curve of Q. Okay, so this is the question for state-to-state transformation. And then we saw also how can we construct the whole set of all possible Qs that you can reach. And to do that, you need to find some special states, which are the vertices of the set of this thermal cone, the set of all possible states that you can reach. And to do it, you need to construct these probabilities P of pi prime, which are called the maximally beta ordered states, which are associated to P. And what do? You take P prime any beta order, so any ordering of your indices, not the one necessarily that you see here. So you take any ordering that you want, and then you take as x points just the partial sums according to that ordering, and as y points, you just take the y point of the quasi-probability, the y point of the thermal majorization curve of P. So in this case, I took some ordering, some other ordering, so this fixes all of the x points, and then as y points, I just take the corresponding y point of the curve of P. And we saw that this is basically the best state that you can get with a different beta order. And as you construct all of them, you can construct all of the vertices of this set. And then you basically characterize the set of all possible states that you can possibly reach by any possible thermalization process with small bath, big bath, whatever. Okay. So now I left at the end a practice question. So I don't know, it was just yesterday, so I don't know if any of you had time to look at it. However, if you would like to quickly discuss it, or if someone would like to, either tell me what's the solution that you found, or if you have some doubts about this problem, we can briefly discuss it together. So you can raise your hands using the participant menu, and then Gabriel will unmute you and you can intervene if you want.
So nobody wants to discuss this?
Okay, I mean, we can also, of course, discuss it in the next classes if you want to come back to this. Yeah, feel free to remind me at the beginning, say, of next class, or I mean, till Friday, that's all right. But yeah, it should be relatively simple. But if you have some doubts about the question or what I mean, please just send me, contact me either during these classes or privately. That's both of them work. So if there are no questions about this problem in particular, I will move forward.
So Matteo, there's actually a question on YouTube, which is kind of a review of last lecture. Maybe that should be useful. So it's from Giorgio Olimpio. He's asking, what is the main difference between TP and TO? As far as I understood, TO are CPTP, Gibbs preserving and time translation covariant, but TPs are also satisfy this condition. So what is the specific difference? I guess that could be like a good review of last lecture.
Yeah, so yeah, what you said is exactly right. And I mean, it's not very obvious what's the exact difference. So I think there are special constructions of counterexamples of things that are TP, but they are not TO. So they're thermal processes, but not thermal operations. But basically, yeah, the two core properties of thermal operations are also respected by, are shared between thermal operations and thermal processes. So it's not very obvious what's the difference, maybe, and the constraints that we know actually work for both sets. And what's certainly true is that at the level of population, so only the transformations between diagonal states, so somehow the energetic part of the theory, this is exactly the same between the two sets. Whereas it is not known if the transformations between involving off-diagonal states, which are also transformations we're going to look at now, if they are the same under thermal operations and thermal processes. So it could be that they're exactly the same, even if the sets may be slightly different, but we it's not known. It's an open question within this framework. So yeah, we don't know exactly. If you mean physically speaking, it's not obvious what's the difference. They may even be basically equivalent as frameworks, even though there is no formal proof.
Cool, thanks.
There is also a question on the chat. Is it possible to do the same construction thermal majorization for infinite dimensional systems? So I think there was also a question, similar question in concerning majorization. So there are some works that deal with majorization in infinite dimension. And in principle, you could also then extend to thermal majorization in infinite dimension. But I'm not an expert on this, and there may be subtleties at play because of the fact that you have, you need to define appropriate measures and so on. So in principle, yes, it should be the same, but then, yeah, there may be fine prints in it. So there is another question, which is, somehow this majorization is a maximization technique. Does this have any relation with the uncertainty principle? I'm not sure about both actually questions, in which sense it's a maximization technique. Yeah, maybe if you want to follow up on that, or maybe at the end we can discuss it further. I don't know about the relation with the uncertainty principles. Thermal majorization holds between classical stochastic processes. So kind of without saying anything about quantum mechanics, really. So it appears to me to be quite independent of the quantum uncertainty principle, if you mean that. There is another question. I have a question about the thermal cones. How does non-Markovian effect affect the thermal cone if they do? Yes, so next class we're going to talk about that. And yes, you need non-Markovianity to reach some of the points in the thermal cone. And this is what we will point out next time. Another question is, what is the physical intuition behind the condition of thermal majorization? What's a physical intuition? So it's a little bit like with majorization. So with majorization, what you do, you're taking these partial sums, and you look if, so X majorizes Y if all of the partial sums of X when you sort it are bigger or equal than all of the partial sums of Y when you're sorting them. And basically this is capturing the idea of X being more less uniform, so more peaked than Y, no? So we know that the distribution 1, 0, 0, 0 is majorizing any other distribution, and the distribution which is totally mixed is majorized by any other. Now, what you're doing here with all of this Gibbs rescaling is that your uniform point is not really the 1 over D, 1 over D distribution. It's actually the thermal distribution. So it's a little bit like you're doing majorization, but you're shifting your reference point. It's majorization with respect to a new point which you deem to be the one which is maximally disordered, which in this case is our equilibrium point, which is a thermal distribution, not a uniform distribution. But apart from that, many of the same intuitions apply. We will see that you can define free energies that are monotonous and all of the things that we did with majorization. Just everything is shifted because our maximally mixed point is now the equilibrium point, so a Gibbs state. I don't know if that answers the question. There is one more.
And Loro has raised his hand.
Yes.
So, Alessandro, you want to go ahead? Oh, okay. So you lowered. Okay, so he lowered his hand. Sorry.
Okay. Okay. There is, meantime, another question. Does the projection scales as a power of n? What projection? sorry, I don't know. In B. Are you talking about this practice now? The how does it change with the number of repetition? So you should see that this is scaling exponentially with the number of repetitions. So meaning the residual, it's just going to be exponentially small. Most of the population is going to be in the ground state if you do this protocol and you repeat. All right. No worries. So, okay, let me move on then to this class, which is about the role of coherence in quantum thermodynamics. And so we're going to look at different things. First of all, we need a little bit of tools to actually talk about these problems. And these tools, I think, are actually quite interesting per se, beyond this thermodynamic application, which is basically an extension of Noether theorem to open systems. So we will see how this theorem can be extended to situations where you have open systems, so you don't have conserved quantities, but you can still make some predictions based on the symmetry of the systems. Then we will talk about this conditional time translation symmetry that we saw already for thermal operations, thermal processes, and we will now kind of unpack the thermodynamic implications that are hidden inside this property of these thermalizations. And we will see that it implies that we need to rethink the way in which we define thermodynamic constraints, and you need new constraints that are able to capture the presence of quantum coherence or superposition between energy levels into the system. And there are a bunch of other consequences which are interesting for work extraction and the way free energy behaves. And finally, we will see how we can actually construct new thermodynamic constraints, and we will see how this work in practice. So there was a question in the chat: for two states to be compared using thermal majorization, do they need to be diagonal in the same basis? So we will see in a moment. So before I only talked about states that are diagonal in the same basis. Now we will see what happens when they are not diagonal in the same basis, and we will see what role thermal majorization still plays in that setup. So hopefully will be answered as we go along in this class. Okay, so let me start with a quick overview of what is that we are gonna actually look at in more detail. So the kind of example you can have in mind is just imagine that you have a quantum state, say for example a pure state in the easiest of cases, which is a superposition of two different energies. Okay. So now this means that the associated density operator, rho of 0, it's gonna look like this. You're gonna have on the diagonal the population, which in this case is just 1/2, not 1/2. And in the off diagonal, you have the coherence. So this is the kind of stuff that we've been talking about so far, which is what I'm referring always to as population. So the occupations of different energy levels. And then this other term is the coherence, what I call coherence, which is just, how much the state actually contains a superposition between two different energies. Okay. And as you can see, you can kind of think about the state as this diagonal part, which is this rho of P. So this is the P that we were talking about so far, plus everything else, which is the coherence, which is the off-diagonal elements in the density operator. So the question that we're asking is really the following. So if your rho of T, your state after some time, is given by some map, CTP, so your thermalization process applied on rho of 0, okay? So now I get a final state that I can also decompose as some rho of P of T plus now some C of T, okay? And now basically what's gonna happen is that in terms of knowing what can happen on the diagonal, thermomajorization is going to be the answer. So you're going to have that this probability here, P of 0, should thermomajorize the probability P of T. And that's fine. But then the question that we have not talked about is, what about this C of T versus C of 0? Okay. So you may say, well, okay, there is always a trivial condition, which is that the state should be, should be a quantum state. So it should be positive. So it means that not everything can happen on the diagonal and on the off diagonal independently, because you may have something which is not a state anymore. However, what we will see is that this condition is insufficient. And what you really need is thermodynamic constraints for coherence. Okay, so this is kind of the general situation, and this is what we will be talking about in this class. How do we actually know what kind of final coherence can emerge from a thermalization process? To discuss this question, we need a little bit of extra tools, which is we need to talk about Noether theorem. So, so the way we can talk about it is that, so Noether theorem is a theorem that relates the existence of a certain symmetry in the system with the existence of a conservation law. So the way it could be formalized is that you have a group G, which is a symmetry group. And then to each element of this group, you're going to associate a unitary, which is just the way in which this group is acting on the quantum state. So in jargon, this is called a group representation. Okay. So if this is a rotation, this is just a unitary on the quantum state that is, applying their rotation, for example, if G is the group of rotations. Of course, the action on density operators is by conjugation, as always. Okay. And because this kind of expressions appear all of the time, it can be useful to just, kind of shorten them in this way. So by this curly U, this is what I will mean. Okay. So now we've got this group, and let's talk about symmetries starting with closed systems, because closed systems is a situation that should be more familiar to everyone. And then we will see how we generalize to this more general setting where you've got open systems. So, so in closed systems, of course, the kind of dynamics that you've got is unitary. So you got a unitary V. So this represents a dynamic that your system is undergoing. So it's evolving under its own Schrödinger equation. And we say that this dynamics, this unitary, is G-symmetric if your unitary V commutes with the unitary operator that represents the symmetry. So in this case, UG. So if this is 0 for every G in the group. Okay. So an example, maybe the simplest example, is that G is a U1 group, or maybe G is R, it's just translations in time. So then your UT, which is representing how you translate a quantum state in time, it's just going to have this kind of form. So you got the Hamiltonian of the system. So e to the minus I HST. And then Noether theorem implies that there are certain conservation laws. So in particular, if I have my quantum state at time 0, and I look at the average energy, or in fact, I look at any moment of energy. So this K can be 1, 2, 3, 4. This is equal at the beginning and at the end. Okay, so we have a conservation law. Okay, so this is very nice. We have a very satisfactory situation. Every time we have a symmetry, well, a continuous symmetry, which is in fact a Lie group, we can associate to this a conservation law, and that's everything. What is that we want to do now? We want to apply this kind of reasoning to thermodynamics, no? Because we have a symmetry, as we saw in the previous class. However, there is an immediate problem, which is in thermodynamics, we are dealing with open systems. Okay, what's the problem with open systems? Well, with a system that is open, in general, we don't have conservation laws. Why we don't have conservation laws? Well, think about energy, for example. So here we had a conservation of energy, but you know, if the system is open, it's interacting with an environment, it's going to exchange energy with the environment. So energy is not going to be conserved on the system. So we cannot hope to get conservation laws. And the same goes if we have other charges, if we have particle number or other things, okay? So the issue is that it seems that we have no Noether theorem. We have no way of extracting information from a symmetry. So, and this is where now we try to rethink what's happening, and we see that we can still actually extract a lot of information from symmetries, even in open system dynamics. It's not going to be conservation laws, it's going to be monotones. So what's first of all, let me formalize the notion of asymmetry in an open system dynamics. And as you will see, you should keep in mind this formalization for closed systems, because it's going to be really closely analogous. So what's now that is going to represent our open system dynamics in general? So we saw unitaries for closed systems. Now for general systems, we're going to have channels. As we saw in the last class, these represent very general set of dynamics for systems, which include unitaries, but includes much more general objects, okay? And our thermal operations and thermal processes in particular are channels. So we need a notion of what it means to be G-symmetric. And you're not gonna be completely surprised if I now say that it is symmetric if it commutes with the unitary for every G in G. Again, you have a symmetry group, and this is the unitary representation like before. What do I mean? Let me write this equation explicitly. I mean the following equation. Okay, this is what it means for them to commute. Okay, and again, remember what we mean by this curly U. We just mean the way unitaries act on the density operator. Okay, and this condition here, it should really remind you this condition here. Okay, so this is what it means for a dynamics to be symmetric. No? And now, instead of conservation laws, we are going to have something which is asymmetry monotones. So we don't have quantities that are constant in time, but we have quantities that are always decreasing in time. Or better, with quantities that under any operation decrease. So as an asymmetry monotone, it's a functional A such that A of epsilon of rho is smaller or equal than A of rho for every rho and for every epsilon which is G symmetric. So why it's called an asymmetry monotone? Well, asymmetry is measuring how much a state. It's going to be a measure of how much a state breaks a symmetry. And then if you do a dynamics that has that symmetry, it cannot increase the asymmetry of the state. So this is the intuition behind this kind of quantity. So if you have, if you use maybe, of course, these are quantum states, but the way you can imagine this is that if you have, say, a pointed object, so this is not going to be invariant under, say, rotations, okay? But then, so it will have some amount of asymmetry. But then, if you do a transformation that preserves the symmetry, no, you can get to a state which has less symmetry, say a sphere. That's all right. But you cannot start with an object which is symmetric and then apply a dynamics which has a symmetry and create something that breaks that symmetry. This is not possible, okay? And this is a very qualitative understanding, but these functionals, I'm putting numbers, are kind of quantifying this notion in a more precise sense, okay? But let me give you an example, a concrete example. This is the relative entropy of a symmetry. Okay, so this is going to be a functional on the state, so it's going to give a number for every quantum state, and it's defined as follows. Is the relative entropy between rho and this dg of rho, which I'm now going to tell you in a second what it is. Well, first of all, let me recall what the relative entropy is. The relative entropy between two states, x and y, is defined as follows. It's a trace of x log of x minus log of y. Okay, so this is called relative entropy. And now, what is this d of g? It's just a group average. So you take rho, and then you average over all possible group elements. So if this is a rotation, you're taking your quantum states and you're averaging over all possible rotations of that state. Which, as you can imagine, this is going to be a symmetric object because you're average over all possible rotations. So at this point, the final output that you get is something that is symmetric. And this asymmetry is basically measuring a distance between rho and d of rho, which is in a sense the closest state to the set of all symmetric states. So these are all symmetric states. This is your rho. So d of rho is going to be some state which is symmetric. And this asymmetry is in a sense measuring, it's not a distance, but intuitively it's measuring the distance between rho and the closest symmetric state. Okay, which of course it's giving you a measure of how asymmetric your state is, how much it breaks your symmetry. Okay. And by the way, this is something that one can check. It has also a different expression that only involves the von Neumann entropies that you saw in the previous classes, which it looks like that.
So Matteo, I'm sorry to interrupt.
Yeah.
Not that this is particularly important, but the bottom right corner of a screen, at least to me, it's cutting a little bit. Where it's written log y, it's somehow cut a little bit. I don't know if you see that, or I don't know if other students also see that. Okay, now it's back. Okay, yeah. And
Okay, so
now it's
it
green.
does affect my position. Okay, is it okay now?
Yeah. So now the screen is very green.
Now
It's
the
like
screen.
completely green. So it fixed, and then okay. So now it seems like it's loading somehow. Part of the screen is now green. Yeah. So I guess I'm not the only one seeing that.
Maybe we'll just stop sharing and
Yeah.
reshare and see what happens.
Yeah, I think so.
Screen.
Okay, it seems perfect now. I'll let you know if it changes.
Okay, let me try to reopen the chat. Somehow the chat is hidden from me. No.
Yeah, to reopen the chat, I think you have to go on the upper part and.
Okay, now it's good. Okay.
Great.
Hope it's everything is good. Otherwise, please stop me again. Okay, so this is the relative entropy of a symmetry. And now let's see that this is actually giving you something which is not a conservation law, but it's kind of the closest best, which is a monotone. So let's take this epsilon, your dynamics, to be G-symmetric. So assume that it respects the symmetry. Okay, and now let's compute this asymmetry on the final state. Okay, so by definition, the asymmetry of the final state is the distance between the relative entropy between epsilon of rho and this kind of group average applied on epsilon of rho. Okay. Well, let's use the definition of this group average. This is an integral over all possible group actions applied on your state. But now we can use the assumption that your epsilon, your channel, is symmetric. And because it's symmetric, it commutes with your symmetry group. So I can actually exchange these two guys. So I'm going to get the relative entropy between epsilon of rho, and I exchange, and then I just rewrite the integral as one thing. This thing. So now we can use a nice property of the relative entropy, which is true in general, which I'm going to maybe write it here. If you apply a channel, whatever channel, any channel, on both sides of the relative entropy, this guy is going to be smaller or equal than the relative entropy at the beginning. Okay. So the basic idea is that if I have X and Y, and then I apply some channel C, the same one to both, I get two new points, which are C of X and C of Y, right? And then if this was S at the beginning, and this is this relative entropy at the end, S prime, no, S prime is smaller than S. So this property is called contractivity, or sometimes it's called data processing inequality. Yeah, and that's it. So we can use this property here to say that this is smaller or equal than the same thing without the epsilon. Okay, but this was the definition of the asymmetry of the initial state. Okay, so we found out that this asymmetry, relative entropy of asymmetry, can never increase under asymmetric dynamics, which is the definition of what an asymmetric monotone is. So I cannot anymore identify something which is conserved, but I can identify something which is always decreasing, and that's very useful. Maybe I'll also go through another example, which is the quantum Fisher information. So some of you may have seen this because maybe you're working on metrology or you know, in some of your courses. But what I'm doing here, I'm considering a family of states, a unitary family of states, which is just this family here. I'm taking rho and all of its time translations. This is rho t, okay? So I'm starting with rho of 0, and then I'm looking at all of the states which are the time evolved of rho, okay? And now I define a quantity as follows. The mutual information of the, say, the orbit associated to rho at time t can be defined as follows. There is a limit involved. You're taking 1 minus something called the fidelity between rho t and rho t plus delta squared divided delta squared. So this fidelity is also a way to measure how different two states are. And it is formally defined in a kind of funny looking expression, which looks, it's not symmetric, but it is. So this is the fidelity. And this is the definition of this Fisher information. Okay, at this point, it may look a bit random. So, but what's happening is that basically we are taking our orbit of states. So we're taking our initial state rho of 0, and then we're evolving it in time. And now imagine that I'm doing ticks every, say, second, no? So this is rho of 0, this is rho of 1, this is rho of 2, and so on. And I'm looking at this kind of orbit here. Now, what I'm doing here is essentially giving a measure of how much the state changes as my parameter changes. Of course, here I'm going infinitesimal and I'm looking for delta that goes to 0, but this is the basic idea. And the reason why I'm doing this is that what the quantum quantum Fisher information is telling you is how well the parameter t, in this case time, is encoded in this set of states. So that if I just give you any state along this orbit and you need to guess what the time is, right? Of course, the more distant are these ticks, the better it is, because you're going to have better accuracy, because you can more easily recognize if the time is 1 second or 2 seconds. And so the more they are apart, the better it is. The closer they are, the worse it is, because the two states are going to be very similar, even though they have different time. So there are a couple of questions here in the chat. Let me see if there were before. So what's the physical interpretation of this group average? Can it be related to dephasing with respect to the basis of the generators? So yes, so for example, if you take, if your group is just time translations, then you're gonna have an average over all possible time translations. And this is in fact equivalent to dephasing in the basis of the Hamiltonian that generates the time translation. Which dephasing, by the way, means that you take your density operator and you remove all of the off-diagonal elements. You put them to 0. So, so yes, this is true. There is a second question. By considering the operator D as the dephasing map, we have the relative entropy of quantum coherence, a quantum coherence measure. And then in this case, the quantum coherence can be seen as a type of asymmetry. So yes and no. So it becomes slightly technical, but let me say that it's basically there are two notions of coherence. One is very kind of computational. You just say quantifying coherence in, say, a fixed basis, okay, and you don't care, say, what's the energy of these states, no? Whereas if you quantify coherence in the sense of asymmetry, as I'm doing here, it's very different if what's the actual energy of the state. Just to give you an example, if I have a superposition of energy 0 and energy 1, this is very different from having a superposition of energy 0, equal superposition of energy 0 and energy 1000. For example, this latter is a much better state to do metrology than the former. So this notion of asymmetry quantifies this more physical notion where the amount of energy or charge in your system actually matters, whereas the other notion of quantum coherence that you're probably referring to doesn't care about this. But then there are certain cases in which the two are one and the same and it doesn't matter. Say if you have a single qubit, it doesn't matter. It seems that the relative entropy stands as some standard choice for the monotone that characterizes asymmetry. Why? In principle, one could select another informatic theoretic quantifier being contractive under thermal operations. So yes, you can choose any other quantifier indeed. So maybe the answer is twofold. So first, in terms of asymmetry, this is just an example. And the second one I was about to tell you, it's another example. So yes, of course, you can make many choices. Each of them corresponds to a different monotone. So each of them is a counterpart of one of these conserved quantities. In terms of why do we care about quantifying coherence rather than just defining some other thermal operation monotone, I will go back to this in a couple of slides, because the basic reason is that usually quantifiers that we look at in thermodynamics are free energies or things that look like free energies. And what we can see here, we will see here, is that these free energies are insufficient in the quantum domain. And so this is why we're going through this kind of ideas. But of course, these guys are going to be thermal operation monotones. This is why we are talking about them. Why they are going to be thermal operation monotones? Because of this symmetry that we discussed in the first class, that these thermodynamic operations have this symmetry. Can the quantum Fisher information be considered as a measure of quasi-static transformations? I'm not sure I understand the question, sorry. But maybe we can discuss it at the end. Because of the limit, I don't know, I would need to think. It's really a measure associated to orbit, not to any given state in a sense. Here is constant along the orbit really, so it doesn't depend on time in this case. Okay, there is someone that raised hands, I think.
Yeah, it seems to be gone now. No, there is still a small orange bar.
Yeah, I think someone raised hand and then this came here. I don't know what is it. I need to move away exactly.
Okay, it seems to be gone now. Well, I don't know.
Okay, let's wait a minute, then if it's still there, maybe we'll try to do something about it. So basically, maybe let me just, it will be a bit long maybe to do it. You will find it in the note, but what you can prove is that this guy is smaller or equal than Q of rho comma T. So what's happening is that you start from rho of 0, and then you go to some new state, epsilon of rho of 0, and then there will be an orbit associated to this new state, and this orbit will have ticks that are much closer than the ticks of the initial one. So the state is becoming increasingly worse in encoding time information. So this is what's happening here, which kind of makes sense because we are capturing another aspect of the idea that coherence is being degraded. And we know that if you want to capture time information, you need a state that is not stationary, and being not stationary means to have a superposition of different energies. So to the extent that this superposition is being degraded by an operation that is time translation symmetric, then the state is losing its ability to encode time information. And this is why this quantum Fisher information is decreasing under these transformations. So as you see, we have, instead of conservation laws, we have this kind of new new quantifiers, new monitors. Okay, let me see if I can do something about this. I guess the quickest is the most silly. Okay, so so far I gave you a little bit of let's say a taste of this whole framework that, you know, if you're interested, you can go and look up more about it. Maybe I will add a couple of references actually later. To quantify the asymmetries and basically extract information from the asymmetry of our dynamics beyond a closed system evolution. What we're gonna look at now is how this property is affects thermodynamic transformations. Because the basic link between everything we said and what we said in the previous class is that the property that we call S of thermal operations of thermal processes is the property that these operations are symmetric under time translations. So are G symmetric for G equal to the group of time translations. So explicitly, this is the way it's defined. And this is the way we saw it in the first class. Okay. And the question we're going to ask is, what are the thermodynamic consequences? Okay. Let me start with one, and then we will have a break, which is about the idea of splitting the free energy that you've seen several times, I think by now, into a coherent and incoherent part. So coherent and incoherent free energy. Right. So quick reminder, the free energy, quantum free energy, non-equilibrium, is the average energy of the system minus kT, the von Neumann entropy. Okay, and this is kind of reflecting the same expression that we know classically. Now, it's going to be useful to think about the free energy difference, which is the difference in free energy between ρ and the thermal state. Why is it useful? Well, because basically the minimum is the energy of the thermal state, so it's easier to look at differences from that minimum. okay? And the way I would like to, well, let me, before I put interpretations, let's see what happens. So we can rewrite this guy in this way. First of all, note that I'm in the free energy, I have the trace of rho h, not the average energy of rho. But of course, the average energy of rho is exactly the same as the average energy of the dephased version of rho. Remember that dephasing, which is this time averaging, is put into zero all of the off-diagonal elements. But the energy only depends on the diagonal one. So if you dephase it or not dephase it, the average energy doesn't change. Okay. And then I'm gonna do a simple trick, which is I'm gonna sum and subtract this quantity here. So let me then write this in this way. So here I subtracted it, so I'm gonna sum it over. Okay. And then I have minus S of rho. Okay. So in this equality here, everything I've done is first add this D here, which I can do without changing anything. And secondly, I have subtracted and summed this quantity, which cancel each other. And that's all, okay? Everything else is the same. Okay. But now notice that these first two terms are just the free energy of the disphased version of rho. Or sorry, if I put also, well, okay, the free energy of the dephased version of rho minus the free energy of gamma, plus, well, we have got KT times the asymmetry of rho, no, from this expression here. Which is delta F of D of rho plus KT of A of rho. Okay, now let's interpret what is that we just derived. Basically, what we're saying is that this free energy here can be thought of as a total free energy, which we have additively decomposed as a diagonal free energy, which is the free energy that is only in the diagonal part of the state, no contribution from coherence, which we could call the classical or diagonal free energy, plus the relative entropy of asymmetry. Multiplied by KT, it pops up out inside the free energy. Okay, so it's kind of a classical quantum decomposition of the free energy, which is pretty nice. However, apart from being pretty nice, there is an important consequence of this. So the total free energy delta F of rho decreases under thermal processes. And if you want to actually do it yourself and check that this is the case, one way to do it is to first check that you can write this free energy as a relative entropy. So the relative entropy between the state and the thermal state. So I'm gonna leave you this as an exercise. And then the decrease of this quantity follows, again using the same argument that we used before of the contractivity. So this guy is just KT S of epsilon of rho to gamma. But then we know that thermal processes are such that the state gamma, the thermal state, is a fixed point. So we can rewrite it as epsilon of rho to epsilon of gamma. And now again, we can use the contractivity that we just talked before. If you have a relative entropy and you apply the same channel on both sides of the relative entropy, you're going to decrease the relative entropy. So this is smaller or equal than KT S of rho gamma. And this is just delta F of rho. Okay. Now we know that the total free energy is decreasing. This is something that we kind of also know in general from thermodynamic considerations. Under thermodynamic processes, this free energy, because this is processes where you put the system in contact with a bath at fixed temperature, this free energy must decrease. This we knew. It's in a sense one form of the second law. No? And what this is doing is telling you that if you start, no, now we know from the decomposition before that this is the classical part of the free energy plus this kind of quantum part of the free energy, which is KT times A. So the fact that this sum must decrease is the statement of this result. To say that the total free energy decreases, it means that the sum of the classical and the quantum part needs to decrease, which is this orange region here. No? If I start at this point here, at time equals 0, I know that the sum of classical and quantum must decrease. So the relation that delta F is always decreasing tells me that I cannot go out of the orange region, okay? However, now we can say something more because we know that what we can actually say is that both the classical and the quantum decrease separately. For the quantum one, well, the quantum one is just basically the asymmetry. And we just proved before that the asymmetry is decreasing under any symmetric process, including thermal processes, which, as we know, are an example of symmetric processes. And then for the classical part of the free energy, okay, how do we see that it's always decreasing? Well, we use the definition. This is just delta F of D of C of rho. Now we know that these two guys commute because C is symmetric. Right? And now we can just use the previous result, no? Because we know that these free energies must be decreasing on every state, including the state D of rho, no? This is just the free, what we wrote here. Maybe I should rewrite this slightly differently. It's just the free energy of C of delta of D of rho. And we know from this relation here that the free energy is always decreasing, the original free energy. So this is smaller or equal than delta F of D of rho, which is delta FC of rho. So now what we showed is that both the classical and the quantum part of the free energies must decrease, which means actually we can say something stronger than just the free energies decreasing, which would restrict us to this orange triangle. We can say that both components must decrease, which then restrict us to this red region here. Okay, so this is an example where using the symmetry considerations, you can start with this well-known relation and make it stronger. So from this kind of constraint to this kind of constraint here. Okay, so I think we should have a break now, maybe till 15 past. And then I'm going to show you a few other physical consequences of the symmetry that is hiding inside thermodynamic processes. In the meantime, if you have any questions, please feel free to write them in the chat or raise your hand and I will take them after the break. All right, guys. I hope everything is okay with audio, video, everything. If not, let me know. So there was, in the meantime, a question. Hey, Matteo, all of this is from the same paper on extending Noether theorem, or is this free energy part an application of that done elsewhere? So first of all, so here I added actually this couple of references. So the first one is the paper that is being referred to here on extending Noether theorem. There are many more, but this is, I think, a good place to start if you're interested in this topic. And in terms of decomposing the free energy, there is this paper by Janzik and a more recent paper by some collaborators and I, which is this one here. And yes, where it's basically an application of the general framework. Yes. Okay. If there is no other question, let me move on. And actually, I'm going to discuss a point that a little bit came up in another question, which was about somehow can we just use thermal operation monotones, which the answer was yes and no, in the sense that yes, all of this framework that we looked at, it's a way to construct new thermal operation or thermal processes monotones, which are based on exploiting or extracting the consequences of the symmetry of these operations. And what I would like to quickly tell you now is why the kind of reasoning that is usually based around the notion of free energies or extensions of the free energies in thermodynamics is insufficient if we look at transformations between quantum states where there is actual superpositions between different energy levels. And to see that that's the case, you can consider a very simple example, which is consider the following transformation. So I start with some state, for example, 0, some single qubit state if you want. And then I bring in a battery system which contains energy W. So one way in which you can phrase this, if you want, is a two-level battery system, which was one of the ways in which Nicole formulated the notion of work, if you remember, one of the previous questions. So you imagine that this is an Hamiltonian, which is just W, W, W. So there is a 0 here and a gap, which is W. And the system is completely excited, okay? And this W can be as big as possible. And this is some amount of energy that you're putting into the system, and it's basically work because it's, it's just energy that you can exploit that is inside this battery that you can pump into the system. And now the question I'm asking is whether there exists a thermal process such that it maps its initial state in the following state, an equal superposition of 0 and 1 in the qubit. So say the qubit is some qubit with some energy gap, which we may fix to 1. Okay. Tensor 0. Okay. So I'm allowed to completely use up the energy of the battery, and I want to create some superposition. So I start from 0, and then I want to create a superposition of 0 and 1. Okay. And the question, of course, in thermodynamics is to give laws or constraints that are, letting you to decide if such a transformation is possible or not. And usually, these kind of constraints are based around the idea of a free energy functional. Now, free energy functionals may be very different from each other. Now, there is a super standard one, which is just the average energy minus KT, the entropy. But there may be many others. You may have heard of generalizations of the free energy. Nicole mentioned some of them based on their Rayleigh entropies. But there is something in common to all of these functionals, which is if you add an unbounded amount of work, this kind of functional should grow unboundedly. So the more work I put, the bigger the free energy should be, which we may phrase as this kind of condition here. Okay. Why? Because the more energy there is in the battery, the bigger should be the free energy of the battery. And I can make this free energy as big as I want by putting as much work as I want, no? But then, if that's the case, for W big enough, I would get to the conclusion that f of 0 tensor W is bigger or equal than f of the superposition here that I can call plus tensor 0. Okay, meaning that the free energy at the beginning is bigger or equal than the one at the end, so that the free energy is going down, which is what the free energy should do. So whatever free energy I define, I know that the constraint associated to that free energy will be satisfied if I put W big enough. Okay, so the free energy tells me you can do whatever you want as long as you put enough work into the system. Instead, adding the symmetry consideration tells us a very different story, no? Because this asymmetry here, we know it must be non-increasing under any Fermat process. But at the beginning, this was 0 because this is a diagonal state. And so it has 0 symmetry because it's stationary under your group, which is time translations. And this is, of course, smaller than the asymmetry of plus tensor 0 because plus is not stationary. So it contains some degree of asymmetry. And in fact, in this case, it would be something like log 2. Okay. But then, using our now asymmetry constraints, we know that for every W, so independently of how much energy or how much work I'm pumping into the system, this transformation cannot be done by Fermat processes. Okay. So what this is telling you is that despite the fact that every free energy condition will be satisfied, whatever is my free energy functional, just by putting as much work as I want, I will not be able to satisfy the symmetry constraints. So this is really telling you that you should somehow think about carefully about the way in which energy and coherence evolve under these thermal transformations and quantify both of them and potentially quantify them separately, okay? So this is the basic idea of this argument here, okay? All right, so this is why we came across now these funny functionals, which really do not look like free energies at all. We kind of have to introduce this kind of function. That's the bottom line, basically. Okay.
Matteo, maybe if I may interrupt for 1 second, there was a question on YouTube, and sure. I delayed myself in asking. So Matteo Savi is asking if you could briefly explain the triangle again that you're talking about before the break. So this is still a question about the pre-break part.
Okay, so this was about the fact that it's well known that the free energy of a system must decrease, a quantum free energies must decrease under thermal processes, because this free energy is getting degraded by the interaction of the system with the environment. Now, what we did in the previous slide was to see that actually this free energy could be regarded as a total free energies, really, because it's a sum of the diagonal part and the off-diagonal part, a classical component and a quantum component. Now, if I do a graph and I put on the y-axis the classical component and on the x-axis the quantum component, The condition that this total free energy decreases is going to define a triangle within this plane. So if I start with, in this example, I'm just starting with this amount here of free energy at the start. And, all of the points that I need to reach are all of the points that have at most the amount of free energy at this point. And this defines a triangle because the total free energy is just a sum. And then the condition that this sum must decrease defines this region. However, what we saw is that in reality, both these two components, the classical and quantum components, must both of them independently decrease under any thermal process. And what this means is that actually I cannot reach any point of the triangle because, for example, I cannot reach this point here. Why? Because, well, the total free energy is decreasing, but in this case, I would be increasing the classical component. And so this thing is not possible. And why is not this thing possible? Say I go to this point in the orange triangle. Well, because here I would be decreasing the total free energy. However, I would be increasing the quantum component of the free energy because I'm moving right. So I cannot move up and I cannot move right. This is what the independent decrease tells you. And this identifies this smaller red square. And this is just showing you how you can apply symmetry considerations to, for example, some inequality that is well known and make it stronger, by seeing that actually this free energy is made of independent components that must both decrease under any thermal operation or thermal process.
Cool, thank you, appreciate it.
All right. Okay, so let me go through another consequence of symmetry, which is about this idea of extracting work from coherence. Okay, so what does it mean? So I'm giving some state, rho, okay, and this state may be a superposition of different energy states. And now I start with a battery system, which is initially in the ground state, and I want to charge up this battery state. So what is that I do? Well, I let the system thermalize, and I hope that by thermalizing it, I can also raise this battery from 0 to some W, okay? So I'm consuming a resource because I started with a state that was out of equilibrium, and I end up with a state that is in equilibrium. But I hope that in the meantime, by using a thermal process, so I'm also being aided by a bath, I can charge up a battery to some extent. Okay. Now, what's the expectation? So what expectations do you have for how big can W be using standard thermodynamic considerations? So it's a work extraction process where you're using a battery, where you are extracting energy of a system using an environment at constant temperature. So what's a famous relation that tells you what's the maximum amount of work that you can get? Yes, the change in free energy, no? And in principle, actually, we should be able to reach it. There should be an optimal protocol that actually can extract the free energy difference. Okay, so there was a question again, actually, about the battery example. Is in the battery example, therefore we are getting outside the red square? Yes, a way to see it is that, yes. So So the expectation is that if I do work extraction, I should be able with some optimal protocol, maybe it's complicated, but in principle, I should be able to do it, to get an amount of work out of a system that it's equal to the free energy, okay? But then what we're gonna see easily is that only the classical component can be extracted. Can be extracted as work. Okay, so W is actually going to be smaller or equal than the classical part of the free energy. Let's prove it. So what is it we're doing? We're doing a thermal process that maps rho tensor 0, 0 into gamma tensor W. Okay, but now we know, we just proved it in the previous slide, that the classical free energy must decrease under this process, which means that the classical free energy of the initial state, which is rho tensor 0, 0, must be bigger or equal than the classical free energy of the final state, which is gamma tensor WW. Okay. But now we can rephrase this as follows. I have the classical free energy of rho, which must be bigger or equal than the classical free energy of W minus the classical free energy of 0. Now remember that the classical free energy was just the free energy of the diagonal state, but these are both diagonal states. And basically the free energy is just energy minus entropy, but all of these states have 0 entropy because they're pure. So everything is just going to boil down to the energy difference between W and 0, which is just W. Okay, and we just got the equation that we wanted. W is more or equal than the classical part of the free energy. So we have this free energy that has the classical and a quantum component, but only the classical component can be extracted as work, whereas the quantum component, which is in coherence, is locked. So this is why this phenomenon is called work locking. Of course, we know, you may have heard about works where you do extract work from coherence, but the extraction of work from coherence requires some extra resource. And basically, because this whole argument follows because thermal processes are symmetric, it means that you need something that breaks this symmetry to be able to extract work from the coherences. So what is that breaks the symmetry? Well, for example, a state that does not commute with its own Hamiltonian. So a state that is not stationary. This is sometimes called a quantum reference frame. Or in the context of time, it could be called a clock that you saw maybe in Nicole's classes. So you need some extra resource. Sometimes this resource is actually implicit. It's not very obvious that you're using it because in some frameworks, you're actually using some classical fields to do work extraction. So it's actually this classical field that you may imagine as some coherent states if you've done some quantum optics, which is a state which is, of course, not stationary, which is allowing you to actually get this coherence out. But you need some non-thermal resources to be able to do so. There are a couple of questions. Is there any relation between Jasinski equality and what we have here in this case? So Jasinski equality, so there are two forms. There is the classical one, and then there is the quantum one. in the quantum one, the way you're doing it is by doing, well, typically you're starting with a Fermat state, okay? And here we are doing a bit of a different scenario. And so you're looking at how much work you need to put to bring a system out of equilibrium. If you wanted to apply the Jasinski equality to this case, you would need to somehow extend it to a case where the initial state, as you see here, is out of equilibrium. And this is not very obvious how you do it, because the classical scheme that you use, as you saw in Nicole's lecture, is called the two-point measurement scheme, where you're doing a projective and measurement of energy. And now if you do a projective measurement of energy to know what's the initial energy, the projection is going to kill any of the diagonal elements in your system. So it's going to kill the coherence that you actually wanted to extract. So this goes into a whole issue that, if you want to define work fluctuations, you need to do measurements, but the measurements are killing the coherence, and the coherence had some effects, some thermodynamic effects. In this case, you may want to consider, trying to extract them as work. And now if you kill them at the very start, you can't do it. So, so yeah, the situation becomes a bit more complicated. What's certain is that if you do energy measurements at the beginning, then of course you cannot extract coherence because you're destroying coherence at step 1 of your protocol. No worries. So sorry, could you repeat how you got to the last line from the previous one? So from this to this. So, okay, so what happens here is that, okay, this is not always true, but this classical free energy for this state here can be split into the classical free energy of rho plus the classical free energy of 0. And the same happens here. The classical free energy of gamma plus the, sorry, free energy difference, because everything, this is delta, everything is relative to the Fermat state, plus the free energy difference of W. Now, the free energy difference of gamma is 0 because it's a free energy of gamma minus a free energy of gamma. So this doesn't appear anymore. And the free energy of 0 on the left-hand side, I brought it with a minus on the right-hand side. Cool. Is it true that one could, however, extract work from coherence between the generate eigenspaces? Yes, so the classical free energy is the free energy of the D-phase state. Dephasing, and this again, I guess goes back to that question about the difference between asymmetry and coherence. So dephasing, it's about removing off-diagonal elements between different energies, okay? But, if I give you a system which is in state plus, and now I give you a second system, so I have 2 copies. Now, there will be a space, which is the one spanned by 0, 1. So the first qubit is in 0, the second in 1. 1, 0, the first qubit is excited, the second de-excited. These have the same energy, no? So if I now apply a dephasing, this is not going to get killed. So if I write the density matrix of this guy, I have something like, I have a 4x4 matrix. I have blocks like this, 0, 0, 0, 1, 1, 0, 1, 1. If I apply the dephasing, what the dephasing is doing is to put to 0 all of these terms. One more. But it is not putting to 0 this term and this term, okay? So, so these are not killed, and this can be extracted. So this coherence, which is coherence within the degenerate subspaces, as Giovanni asked, can actually be extracted. This becomes actually relevant where you start to think what happens in this case when n becomes very large, and you suddenly start to see that actually most of the free energy is in the classical part, and the amount that is, so basically the classical part of the free energy grows linearly, and the quantum part grows only logarithmically with n. So it becomes more and more negligible compared to the classical part. And this is another way to see why, when you go into the macroscopic limit, actually all of these considerations becomes negligible. We never talk about, oh, what's the classical and quantum component of the free energy when we talk about microscopic thermodynamics. And the reason is, if you have many systems, actually all of the free energy is classical free energy. And work locking is telling you, oh, some negligible part of the free energy cannot be extracted, but it doesn't matter.
So Matteo, there's also a interesting question from Junan Lin in YouTube, which is it's kind of a curiosity. So he's referring to the example that you gave previously, where one maps the 0W state to the plus zero, right? And essentially the argument is that this, from a quantum information perspective, this would be a very easy operation to do. You just do a Hadamard and an X gate.
Yeah.
But from a thermodynamic perspective, somehow this is impossible. So I guess the question is essentially, if the intuition is really that you need an extra resource, like you mentioned in the next slide.
So yeah, so I think it's a very it's a good question. It's a very subtle topic. So the way you would do it, no, you say I do another map on the first system. It goes back to my comment about you're assuming that you have access to classical fields, and that's all fine. I can imagine that basically I say, okay, I do the other map on my state 0, so I make it plus. But then if I wanted to actually say, well, how is this actually happening? No, okay, I have a description where I have a laser field, and that laser field is quantized, so I can introduce the state of the laser field, and maybe some coherent state. Maybe alpha is very large, so it's a very kind of macroscopic field, classical field in a sense. And then I have the 0 guy, and then I have some big Schrodinger interaction between the two, which is basically more or less doing a unitary on the system once I trace away the field, no? And then you could say, okay, this is simple to do. So what's the problem? The problem is in thermodynamics, we are interested in bookkeeping. So we want to know how much resources we have spent, no? And for example, if you apply to the case of work extraction, you say I apply some classical field and I get work out of coherences, no problem. No, I do the other math and I get the work out. However, what's probably happening is that if you do the full picture, you get that this state, then your coherent state of the field is becoming something which is, let me call it, I don't know, raw alpha noisy. Some very small epsilon noisy, some very tiny small noise in your field has been accumulated by doing this process, no? You say, okay, but this noise is very small. However, also the work that you extracted is very small. You just extracted work from a single qubit. So you extracted a microscopic amount of work and you put some microscopic amount of noise in your classical field. And now, so you maybe increase its entropy. So the problem then becomes not to neglect the things that we don't like and we keep the ones that we like. We extracted some negligible amount of work and we maybe made a negligible, put a negligible amount of noise into the classical field. And if you want to actually extract a lot of work, you would need to repeat this process many times. And then maybe this noise becomes epsilon and then plus epsilon plus epsilon, or it could become very large by the time that the work has become large. So that's why one needs to be a bit careful in these bookkeeping operations, no? But then in quantum information, we don't care at all about all of this. No, we are very happy to spend a huge amount of energy to just, shine our lasers, because energy is not a resource in that context. We only care about that the unitary is done well with good fidelity, and then all of those considerations never enter into place. So yes.
Cool, thanks.
Okay, so let me move on to how do we actually get some extra constraints in general on these systems. And one way to think about things which is quite useful and goes back to a question that was asked about what's the role of thermomajorization, is to think in terms of modes of coherence. Okay, so what are modes of coherence? One way you can think about it is basically you have a system. Say I have a 3-level system, and then I'm going to look at all possible transitions between energy levels. Okay, so all possible energy gaps. And the set of all possible energy gaps, I'm going to call modes. Okay, so I'm going to write it now in math. So this is the set of omega such that there exists some energy EI, EJ in the spectrum of the Hamiltonian, such that omega is just the difference between these two energies. I'm just saying it's a set of all possible gaps in your spectrum, in your quantum system. Then, if you do that, you can decompose rho as a sum over all modes of this quantity here, rho of omega. What is this rho of omega? Well, it's all of the parts of the state that are transforming under time translations with speed omega. So they take a phase equal to omega. Example. Take an harmonic oscillator. The spectrum is going to be just equally spaced spectrum. So N, E, N, N. So you go on. So this is E. Okay. So what are the modes? Well, all possible gaps. What can the all possible gaps be? Well, all multiples of E, no? I have E, and then I have 2 E's, and then I have 3E. And of course, I can have +3 and -3, depending on how I take, which level I take first and which level I take second. So I have dot, 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 -2, -1, 0, 1, 2, dot, 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 and it goes on and on. No? And now what is rho of omega? It's all of the elements in the density matrix that transform with a given phase. What does it mean to transform with a given phase? Well, it means somehow that the energy difference between the bra and the cat is some constant thing. So I'm going to have a sum over n of rho n plus omega n plus omega n. And if I want to draw it, this means that if I take my density operator that represents my oscillator, I have the diagonal elements. These are mode 0. Why? Because if I look at how they transform under time translations, they don't get any phase. These are the diagonal parts of the density operators that don't get any phase. Then there is mode 1, which is the first off diagonal. Then there is mode 2, which is the second off diagonal, and so on. And then you have mode -1, -2, which is the same, but symmetric under the diagonal. Okay. And maybe a super simple example. So you have if you have a single qubit, I have rho. And then I can write rho as, you have P0, 0, 0, plus P1, 1, 1, plus C, 0, 1, plus C star, 1, 0. And now this guy is the part that is stationary under time translations. If I do a time evolution only on this part, I get the phase 0. So this is mode 0. Then there is one part, which one is going to be? I don't know. So one part now, which if I do a time translation is going to get a phase which is plus omega. So this is going to be mode -1. And if I do time translation on this part, it's going to take a phase plus omega. So this is mode 1. Okay. You can see now that What I mean is that I do time translation of this guy, and now on the left-hand side, I just get identity. On the right-hand side, I just get -1. So I took the Hamiltonian to be just 1. Or omega-1 if you want. So I'm splitting the state in pieces such that each piece is transforming independently in a different way under time translation, and looking at the phase that I'm creating. So why would I do that? Well, the reason is that because under your symmetry condition, all of the modes are transforming independently under symmetric operations. So if you have a symmetric operation, mode 0, and you apply your channel only to mode 0, so you just took, say, mode 0 means the diagonal part. So if I apply the your channel only to the diagonal part, I get something at the end which is diagonal, meaning it's a mode 0 of the final state. If I now apply my channel to mode 1, I get something that is in mode 1. So there is never crosstalk between different modes. So this is what makes them so convenient. Unfortunately, I don't have time to go through the proof of this equation here. But what this is telling you in, say, if you have a qubit, for example, I have a thermal process. It means that the diagonal part of the initial state gets mapped into the diagonal part of the final state. This coherence element gets mapped into the coherence element in the final state, and so on. So to know the dynamics of population, for example, I don't need to know what the coherence is, because these are independent. And this is true not only between coherence and population, but it's also true within this more fine structure inside the coherence, so the different modes. So if I have a Q-trit, for example, with 3 equal gaps, I have the population here. Then I have the elements that transform with given phase, which are the first off diagonal. And then I have the elements that transform with, say, twice the phase, which are these off diagonal. And now under a thermal process, well, these are getting transformed into separately into the same elements of the final state. So the red goes into the red, the blue goes into the blue, and the black goes into the black. All of the equations decouple. Now, why is this interesting? Well, we want to know, so the question that we wanted to answer is, is there a thermal process mapping? So is there a thermal process CTP such that I can map some quantum state rho into some quantum state sigma? And note, now I'm not talking about only populations. So the problem for populations we talked about yesterday, it's fully solvable. But now I'm talking about the completely general problem. And now what you can show is that this is the case if and only if there exists a channel, C, such that C of rho 0, so the mode 0 of the initial state, goes into the mode 0 of the final state. The mode 1 goes into the mode 1, and so on. Plus, of course, we know that we need to preserve the gamma state, right? And now what we can recognize is that actually this problem, this sub-problem here, the part of the problem that involves only mode 0, this is the problem that we solved yesterday. This is the problem that is solved by the thermomajorization constraint, where now I'm using a slight abuse of notation, but rho of 0 is a matrix with only the diagonal, but what I mean is the probability distribution in the diagonal. thermomajorizes the probability distribution in the diagonal, because rho of 0 is just a matrix with 0 everywhere apart from the diagonal. No? So the mode 0 constraint is thermomajorization. But then I also need to ensure all of these other constraints. And mode 1 of the initial states is mapped into mode 1 of the final state, and so on for every possible mode into the system. How do I then check that this is the case? Well, these are going to be controlled by constraints on quantum coherence, such as the constraints that we saw so far, the ones that we build using, say, the relative entropy of asymmetry, the one that uses the quantum Fisher information, and there are many others that you can construct. But basically, these are dealing with this part of the transformation, and thermomajorization is dealing with the diagonal. So even for general transformations, when you go from general state to general state, thermomajorization is going to control what happens on the diagonal, but then you need to add some extra, and that extra are all of these considerations that we developed in this class based on these asymmetry relations. Okay. So, okay, so I left practice for those of you who would like to look at this. It's basically thinking about these conditions for a single qubit. So for a single qubit, you can use something which is called the Choi-Yamorkowski isomorphism. If you remember, you need a channel to be positive. A channel is defined as something which is not just positive, but it's positive also with the extent on when you apply it on joint state of many parties. So for a single qubit, in fact, you can just check this condition here, that the channel extended with identity applied on the maximally entangled state of 2 qubits is some positive matrix. And what you can show is that if your channel is symmetric, this equation here is satisfied. And to check this, you can use the Choi-Yamorkowski isomorphism. And then if you use this condition here, you can in fact completely solve the problem of what processes can happen under thermal, what transformation can happen under thermal processes for a single qubit. Using this condition here, you get all of the conditions that you need for coherence, and you get a complete set of conditions. So this is not very easy, but if those of you that are maybe a bit more expert already, if you would like to do it, it's an interesting problem. How do we define coherence modes when the Hamiltonian spectrum exhibits degeneracies? So in the same way, so it's all of the terms that are transforming in the same way under time translation. So if I go back to maybe this example here of 2 qubits where there are indeed degeneracies, as you can see, actually what you would have here is that the 0 mode, let me erase a little bit. So now the 0 mode is everything that is stationary under time translation. And now it's going to be all of this stuff. So as you can see, there are, in fact, things that are off diagonal, but in mode 0. This is what changes when you have degeneracies. And then there would be a mode 1. That would be like this guy, and this guy, this guy, and this guy. And then there would be a mode 2, which is this one. So you can do the same. You can apply the same definitions, and you can try to draw conclusions from there. Okay, so this is a quick summary of what we've seen. quite a few things. So we saw that we saw already yesterday, the thermal processes are symmetric, so they satisfy this condition here, symmetric under time translations, and this implies a lot of different things. It implies that the free energy or free energies are insufficient, so functionals that increase as you put more and more work are insufficient to to give you thermodynamic constraints on what happens on superpositions. So what you need to do is introduce asymmetry monotons, which take the place of conservation laws in open system dynamics. And we saw a couple of them, the relative entropy of asymmetry and the quantum Fisher information. And these are conditions that need to be satisfied if a thermal process exists between two states. We saw that the free energy, average energy minus KT by Norman entropy can actually be decomposed into a classical part and a quantum part. And what's interesting about it is that you can actually prove that both parts independently need to decrease, not only the total free energy itself. So this is gonna give you stronger constraints. This was a triangle square drawing. We saw that there is this notion of work clocking, whereby the work that is inside the coherent part of the free energy is locked. You cannot extract it as work unless you add some extra razors, like some field that is allowing you to do so. Otherwise, this thermodynamic relation gets deformed from W smaller or equal than delta F to W smaller or equal than the classical part only of the free energy. This we saw quite quickly, but basically this condition of symmetry is equivalent to the condition that each mode of the initial state is mapped into the corresponding mode of the final state. And the thermal majorization constraint can be conceptualized as the mode 0 constraint in these terms, in this situation. So we see that we have actually a hierarchy of conditions that needs to be satisfied, and what we saw in the first class solves the kind of classical part. And then we saw that more constraints can be in fact extracted, like looking at this Choi isomorphism. Well, this we didn't really see, I really just mentioned very quickly. So there are some actually conditions, which is full constraints for thermal processes. This is something I would like to mention for those of you who are interested. I didn't have time to actually go through it, but basically this is a very interesting paper. It's nice because it's giving you a complete set of these monotons here. We only constructed a couple here, so giving you a complete set. What's bad about it, or what's maybe not bad, it's a very good paper, but what's somehow would need to be built upon is that the constraints are still very implicit. So it's very difficult to see what there is inside this very big set of constraints. But yeah, this is a very cool paper. And with this, I finished. So thank you very much again for showing up. And I will stay here for a few minutes more if any of you has any questions about any of the things that we talked about today or yesterday. Thank you very much.
Matteo, thank you so much for the another great lecture. Maybe I can kick off the questions with a question from Frank Steinhoff from YouTube. So Frank's essentially asking about whether there are any results which extend this not only to coherence but to generic superpositions. And I guess in the sense of the resource theory of superpositions, which are more general than just coherence.
Yes, so indeed, you could say, imagine that my system is interacting with a bath and or environment, and that bath doesn't need to be necessarily in a thermal state, but or it is maybe in a thermal state, but it's also has some extra symmetries. For example, say because of its Hamiltonian, it's also rotational invariant, no? And then, of course, the system can exchange angular momentum with this environment. However, there will be asymmetry monotone. So the asymmetry of, in terms of now rotations of the system will degrade in time, and you can capture this through asymmetry monotones. And so this paper that I mentioned about extending Noether theorem, this one here, the considerations here are for general symmetries. So you can actually, if you're interested, it's very cool introductory way to to this topic. And yes, the old framework extends to that.
Cool, cool, thanks. So I guess from YouTube, that's all there is so far.
Okay, I don't.
So everyone,
I hope I.
Oh, sorry. No, just gonna mention, remember to take your selfie and send it to me. I'm building up a web page in the website with all our selfies.
Okay, cool. I mean, of course, feel free to, if you think about some question, you can either drop me an email or at the beginning of next question, please feel free to ask them at the start in the chat. And yes, I think this is everything on my side. Next time, we're going to talk about resource theories and Markovianity, which was actually one of the questions at the start. So yes, so that's the topic next time.
Cool, fantastic. So thank you again, Matteo, and we see you and everyone else tomorrow.
Thank you all. Bye.
Bye bye.